everyone, welcome to the Admiral Code Day 18, Lava Duct Lagoon. In this video, I'll be going over the problem, my approach, and then my solution written in Python. Let's get right into it. So in this problem, the elves are digging a lagoon to store some lava, and we get an input that looks like this, where each line has three things we care about. The first is a direction, the six is a number, the second is a digit containing the number of steps to dig. And then this third part is a hexadecimal code that we're not going to care about for part one, but becomes relevant in part two. So essentially, these first two instructions are plans for the elves digging. So they start in a 1 by 1 meter hole. And then this instruction, for example, they take a direction and then the number of steps to dig. So here we would dig right 6 steps, then down 5 steps, then left 2 steps, down 2 steps, etc. And we're eventually going to get back to the starting position with this final operation. So with this example, we get a lagoon that looks like this. Yeah, and so we can see that start here, dig 6 to the right, whatever it was, 5 down, 2 left, etc., etc. Then we want to fill in the lagoon. We can see that we fill in these empty points. We know it's going to be a loop, and so we can fill in the interior. And then we want to return the total volume of the loop, including its filled out interior. And yeah, let's get right into it. So for this problem, I've got some boilerplate, but then getting into the meat of it in part one, what I'm going to use, maybe before going over the code, let's talk a little bit about the approach to the problem. We are going to use two formulas called the shoelace formula and Pick's formula. And what these let us do is, using these two formulas, we can take this outer loop and calculate the area of the whole of the interior. Why that's relevant is because here we have a pretty small input, so we could just run flood fill or whatever algorithm you want to calculate the interior area. However, we're going to have a much larger input, and so this is sort of impractical if, say, we have a billion interior points, or what if we have even orders of magnitude higher? We can't run like a flood fill or something like that. And so with these two algorithms, yeah, they'll let us compute that area much, much, much more efficiently. So let's look at them a little bit. Pick's formula. Our theorem. All right, so what Pick's theorem does is it takes a polygon with integer vertex coordinates. And so we have this complicated looking thing. Notably, our coordinates for you can think of this as a polygon where the vertices are at wherever we change directions. And notably, yes, these are all integers because the amount we're moving is always an integer. So essentially this formula relates the area to the number of points in the interior, which is I, the number of points in the boundary, which is B, and then some of these constants. So we have A is equal to total area is equal to interior plus boundary over 2 minus 1. And so what the problem here is that we have multiple unknowns. We know the boundary points. It's very easy to get the length of the boundary. We can just sum up over all of these direction counts and then add 1 because we initially start in a dug square. But we don't know the interior points and we don't know the total area. And so to get the total area, we can use the shoelace formula. The shoelace formula takes a polygon like this, like our trench, and then points that are either clockwise or counterclockwise. Um, so we have like these points that are ordered like clockwise. Sorry, in this case, I guess it's counterclockwise. P1, P2, P3, P4, P5, P6. So we aren't like skipping locations along this line. It could not be like, for example, P1, P2, P3, P4, because we were going counterclockwise and then we went clockwise. And so this we have really easily too, because this loop is created by a series of instructions. So we know the clockwise, we know like an ordering of the vertices. Then from this, you can use this trapezoid formula. Um, it's kind of interesting how this actually works. It sort of forms a trapezoid using each of the pairs of points. Um, so for example, P1 and P2 forms like this trapezoid here, shaded, P2 and P3, this area. And if you add up these signed areas, notably signed areas, you can't just naively add up all these trapezoid areas, then you get the area of the shape. Um, yeah, so I mean, that's sort of beyond the scope of this video. But we can look at the formula here. So just a simple sum um, uh, where we take like each edge, so x1 and xi and yi, or each vertice xi and yi, and then the next vertice in the ordering, which would be xi plus 1 and yi plus 1. Perform this little multiplication together, sum them up, and take half of it, and that will give us the area. So now we know the area, we know the boundary, and we can compute I. Then once we've computed I, we can do I, or just return the boundary plus the interior, so I plus B. Yeah, now that we've gone over that, let's show the code to do this. So I create this list of vertices, um, which are of type point, where point is just the x and y coordinate of each vertice. It's relevant that this is a list and not a set because we care about the order of the points. Then we iterate over the input, get the direction and the count using this regular expression. Then we can get sort of from the direction, which is just a character like right, up, down, left. We can use this map here to convert. So up, for example, I see now that this is actually a little bit flipped around, but the math still works totally fine. Like, so up, we're moving -1 in one direction and 0 in the opposite direction, then down is the opposite, and left and right operate up on the second component. I say this is wrong because if you think about this as an XY plane where X goes this way and Y increases this way, up and down should be having 0 as the X component. But since this is, I guess what we're doing here is sort of flipping, like essentially, since we're switching the coordinates, we're reflecting over like a 45-degree line, but it preserves the shape. So the area of the shape is all I care about. It's funny that I've never noticed a little bug until now though. Okay, we use the direction map to get the change in X and change in Y. Then update X and Y, which we're using to count or to track the position as we dig the trench, and then append to our list of vertices. We're also keeping this boundary count, which is just the sum of essentially this column. And then, yeah, so now what we can do is apply Shoelace's formula. We create this list of trapezoids, which starts out with we look at the Shoelace formula. We need to go from P1 to P2, P2 to 3, 3 to 4, 4 to 5. Then we also need this final 5 to 1. And so we're initializing the list with that final last element to first element trapezoid. Then we iterate over, appending to this trapezoid list with each pair of like I and I plus 1 vertices. Then we take the absolute value of the sum of that. Um, so it doesn't have it here, but we need to take an absolute value because it's a signed area and then divide it by 2 to get the full area. Now we apply Pick's formula to get the interior count, which is the area minus the boundary count over 2 plus 1. Here we're just moving things around to get a little bit to isolate I, and then simply returning the boundary count plus the interior count. We can run this example on the example they give us, which is 62, and that is indeed correct. So now moving on to part 2, we have some additional information. In part 1, they told us that this was a hex code corresponding to a color, but in fact, it's actually the true direction and count. So here we can see that the direction and count are actually gigantic, or the count specifically. So a flood fill would not work on part 2. We get the direction by taking the last digit of the hexadecimal, and then we get the count by converting the remaining 5 digits to an integer. So converting base 16 to base 10. Then we just use this new set of instructions and do the exact same logic, count the interior area. So the only difference between part 1 and part 2 is how we're parsing the input. Let's look at how we do that. So we can see that this code is 99% the same. The one thing we're changing is we're pulling out the hex and then the direction, where the direction is the final character. You can look at this regex, but dir is getting this last digit and hex is getting these preceding 5. Then we're using this little trick, casting to an integer, base 16 of the string in the hex variable, getting the change in x, change in y from the direction map, to which I've added 3, 1, 0 to 3, because that's based on these instructions. 0 means R, 1 means D, etc. Then we're doing the exact same thing, where we apply Shoelace's formula and Pick's formula, get the boundary count plus interior count, get this gigantic number. Could never do this with search. 9.5 ends with 1.5. That is correct. So yeah, that does it for this problem. To be honest, not my favorite. If you don't know about these formulas, you just can't do it. This is one of only 2 problems so far that I had to actually look at the solutions to see what people did. And to be honest, I don't think I ever would have gotten this one. I mean, notably in like the pipe problem in, what was it? I don't know, day 10 or something, day 8. That one you could have used Pick's theorem and Shoelace formula also. However, you could also just use search to get the area within the pipes. And so, yeah, I don't know. It doesn't really seem like a great problem when you're just testing your knowledge of these esoteric formulas, that it would be quite a challenge to rederive, or at least maybe you could do it. It would take a long time, and it wouldn't be programming or really problem solving time. Be working on like a totally different problem. But yeah, still made it through this one. Looking forward to day 19. Thank you for watching. If you have questions, comments, leave them down below. And yeah, see you in the next video.